All right, guys, so before we start programming, we've got to get our heads around the main three instructions that we're going to be making use of. One being XIC, XIO, and OTE. Those are our main three. They are found here under our favorites. So if I click on favorites, sometimes you can't click on this until you click on a rung and then it becomes available. So you can see here under favorites, I have an examine on, that's my XIC, examine off, XIO, and then my output is called output energize. They're found under favorites. They're also found here under bit logic as well. So you'll see the main three here, 1, 2, and 3 that are available. Okay. For either of these guys, similar to all the other videos that I've done before and all the other PLC programs, you grab these guys, hold down your mouse, and then bring it down to the rung. And when you see green, then you can let it go and it drops in. Okay, so I've got an XIC here. I need an output on the end here, so I'm going to drop that bad boy down here. Okay, then I'm going to have another rung, so I'm going to click on this rung number. Then I'm going to add a rung here. Okay, I'm going to put the opposite instruction and examine off down here with another output here. And then down below, I'm going to add one more rung here. I'm going to add a standard 3-wire. So I'm going to put 2 XICs, and then I'm going to put my output at the end there. So that's basically an AND circuit there. This and this have to be true in order for this to come in. But I'm also going to put in another parallel rung here. So I'm going to click on this guy, and I'm going to click on this one right here, put in a branch. Okay, once that branch comes in, then you can click on this side right here, bring it over till you see green. Gorgeous. Now we've got a parallel rung to this instruction right here. And I want to put the same type of instruction. I want to put an examine on in parallel with that guy as well. Okay, so we've got an examine if closed, an examine if open, and then here we've got 3 examine if closed going all to an output energize here. So what I'm going to do is I'm going to do like a quick little diagram here to get our heads around these 2 instructions and why we would make use of one or the other. And then in a standard 3-wire, why we would make use of the same instruction right across for our stop and our start. And I'm sure that I'm going to get some dislikes on this video because my way of showing the stop is using an XIC, whereas other people's way of showing the stop is using an XIO. So hopefully I can clear that up as to why that decision has been made on my video. Okay, so let me bring up a whiteboard here. So these guys here are basically the inputs for my PLC and the outputs for my PLC. Right, so this one, this such a long number, 1769 L24 ER QBFC1B. Allen Bradley Compact Logics makes use of DC voltage in and then DC voltage out. On other PLCs that you've seen me working on, they may have had a relay output. This one is a transistor output. So this one outputs, takes a positive voltage into the inputs and then outputs a positive voltage as well, but both being 24 volts DC. Okay, the wiring for these guys is found right here. So this is I put in the Compact Logic's 5370 series and looked for the wiring here. So we can see here that we've got the inputs going into the DC input 0, 1, 2, 3, 4, 5, 6, and 7, and then the common for each of those guys. So you'll see that there's 8 terminals that we can wire to, but as we've mentioned before, they always start at 0, right? So it's 0 through 7. So we have 8 inputs there. You can see here that we have the 24 volt power supply here, and it looks like the 24 volts positive is being applied to each of our terminals of our inputs. So I have some limit switches here, and it looks like they've got some normally open push buttons that have been drawn here as well. Those positive voltages are applied to each of the input terminals. So you'll see that every separate input has a separate device that goes to it. So you don't normally like parallel or series your inputs, like your actual switches on the outside. You bring each individual switch to a separate terminal, and that way you can change the logic without having to change the wiring. So every single input device goes to a separate input terminal on the PLC. In this case, we have positive voltage being applied to the input terminal, And then we have the return being the common here. So the common is going to go back to the negative of our power supply. Okay, if we look at the outputs here, then we have a 24 volt DC power supply. Okay, could be the same, or more likely being the same power supply as was provided for these inputs here. Okay, so we've got a separate power supply that powers this PLC, and we're making use of the positive DC voltage. That's going into this terminal for the positive voltage here. Okay, then we can see here that the DC is brought to all of the different returns for, let's see, control relays and some solenoids here. And each of the outputs, being the control relay or the solenoid, is going to a separate output terminal. So again, we don't have outputs, we never have outputs in series, but we don't have multiple outputs on each terminal. Each terminal has a single output device that it goes to. That way we can change the logic without having to change the actual wiring. So with this one, we provide a positive voltage to positive V terminal. That positive voltage is available to all of these outputs here. And then when the outputs turn on in the PLC program, then that positive voltage will be applied to our external load, being the control relay, or the solenoid in this case. And then all of them are sharing a common return to the negative DC voltage there. All right, guys, so now that we've gone over the wiring or expected wiring on the inputs and the outputs, let's go back to that diagram and let's talk about the difference between XIC and XIO, because those are our main instructions that we're going to be making use of time and time again within our PLC programming. So we'll start off with the examine off closed. So a little bit of a lag as I draw this in and talk to you here. So we've got examine if closed. Okay, that one is termed an XIC, and the symbol for that within our PLC programming in the Allen Bradley environment looks like this. Okay, so it's backwards from the way that you would learn your ladder diagram symbol. So it's an examine if closed, but it's actually drawn as a normally open contact. Okay, the other one that we're looking at is an examine if open. Okay, that one is termed an XIO, and that symbol looks backwards from your open contact. It actually looks, or is drawn, as a normally closed contact. Okay, so each one of these guys is going to look for opposite things within your program. Okay, so this examine if closed looks for the presence of a 1 in a memory. Okay, so we're looking for a 1 in the memory. Now that could be either on the input side or on the output side. But remember, we're dealing with Boolean logic where we have true or false, true being a 1, false being a 0. Okay, so we could also say looks for true. Okay, the XIO is looking for the opposite. Here, let's put some gorgeous line here. Let's see if I can put a nice line across there. Oh, that's gorgeous. Okay, perfect. So examine if open looks for the opposite, right? Looks for the presence of a 0. In the PLC memory. Okay, and a 0 is corresponding to a false status. So we'll say it also looks for a false status. Okay, that's the main deal, in that we have a 1 corresponding to a true and a 0 corresponding to a false. The one that looks for the presence of a 1 is this one, the XIC, examine if closed. And that's because if the contact is closed, then we would have 24 volts being applied to our input there. So another thing we could put here would be, so looks for the presence of 24 volts. Okay, so 24 volts either going into the input terminal or coming out of the output terminal, right? On our outputs here, we could have these guys fired on. In this case, my PLC is using 24 volts DC. Others will make use of a 24 volts AC, but that voltage would be present here at the output terminal, going to the physical load and then turning on the contactor or the relay or the light that's attached to that, right? Whereas on our inputs, the 24 volts would be from our power supply through the switch, and then if the switch is closed, examine if closed, then the voltage would be applied to that input terminal. That input terminal's status would be true, and we would have a 1 in the memory there. Okay, so for the examine if open, it's looking for 0 volts. Looks. Come on, Pete. So saying looks for the presence of 0 volts, another way to say that would be looking for the lack of 24 volts, right? So no voltage being applied to the input terminals and no voltage available at the output terminals. So either here, you can't see that, either here or here we would have no voltage available. Okay, last thing that I would add to this list would be that if there is 24 volts available at the output here, then that would mean that that 24 volts is going to our physical load and turning on the physical load. So this one here also looks to see if something's on. Okay, whereas the XIO corresponds to 0 volts, 0 volts not being able to turn anything on, so that's looking to see if something's off. Sorry. Okay, so let's walk through all the different things that the XIC would be looking for. Okay, so the XIC is looking for a 1 in the memory, which would correspond to a true status, which would also correspond to 24 volts being available. And if 24 volts is there, then something's either closed or it's on in the on status. Okay, whereas the XIO, examine if open, if something's open, that usually means that there is a 0 in the memory of the PLC, which would mean that it has a false status. 0 in the PLC memory means that there's usually 0 volts available either at the input or the output. And if we have 0 volts, that usually corresponds to something as off. So we have 0, false, 0 volts, and off corresponding to the XIO. And then we have 1, true, 24 volts, or on corresponding to the XIC. Okay, and those are our 2 instructions that we're going to make use of over and over and over again. Okay, so let's take a look at some inputs. I'm going to draw some inputs onto this diagram now, and then we can take a look at whether the PLC program is going to be true or false depending on which type of instruction that we place in there. Okay, so what I'll start off with is just some selector switches here. So we've got the input 0 and input 1 there, right? So I'll put in some selector switches. So I've got one that's normally open, and I got one that is closed. And then here for my input 2 and input 3, I'm going to put a normally closed stop push button here. And then I'm going to put a normally open start push button on input number 3. Okay, and hopefully this helps to make sense of the way that the inputs are wired and then what type of instructions you would make use of. Okay, so then in order to wire these guys up, well, I would have my 24 volts available. Let's see if I can put a nice straight line straight down. It's not bad. Okay, so that guy is going to feed from my positive 24 volts, and that's going to feed to every one of my inputs here. So my inputs are going to be sourcing inputs. So this is another discussion we can have later on, like what does source and what does sink mean. But sourcing means that I'm the actual switch is a sourcing switch. So all of these switches are sourcing in that they are providing a positive input or positive voltage into the input terminal of the PLC. So I have sourcing inputs, sourcing like physical input devices, but the inputs on the PLC are going to be sinking. They're going to take that positive voltage and then sink it to ground. Okay, so then I need to just complete this circuit here. So the common here of my PLC would then be tied into the negative of my power supply. So I would have voltage going from the 24 volts and then through this switch, if it was closed, into the input terminal, and then I have the common going back to the negative of my power supply. Okay, here on the outputs here, I'm going to provide the positive voltage to this terminal. So I'm going to come out here a little bit so I have some room, and down to here. Okay, so I'm bringing again my 24 volts into the positive of the outputs there, and then each individual output, I'll just put some lights for now. Okay, so I got a couple LED lights on each guy. Okay, and then those guys would be wired from the PLC to the individual lamps here. And then they would share a common return to the negative of the power supply. Beauty. So now you can see, or hopefully see, that is this going to wipe out the whole thing? No, it's good. Hopefully you can see here that we have individual inputs, right? So we've got each input being like a push button or a selector switch, something like that, going to individual input terminals. And then all of our outputs are going to individual output terminals of the PLC. And now the PLC program is going to determine how the status of these guys determines the status of these guys, right? So we have, again, here we have our inputs on this side, and we've got our outputs on this side. And for this particular PLC, we've got DC being used, 24 volts DC being used for the inputs, and we've got 24 volts DC being used for the outputs. Again, depends on your particular PLC, whether they have transistor or relay outputs, and what can be placed onto both the inputs or the outputs of either one. Okay, so the first one, what did I have in that program? I've already forgotten what I had. I had an examine if closed. Okay, so I had an examine if closed, then examine if open on the next rung. Then we had a 3-wire. Okay, so our PLC program here is that we have for our first rung, we have an examine if closed. Then we have an examine if open. And then we have a 3-wire where we have what's going to be our stop, then our start, then our holding contact, and then we have our output here. So 3 different instructions there. And I'll have to show you like how to put the specific bits and everything in there in a little bit. But let's see if we can get our heads around these different instructions first. Okay, so let's take a look at this first rung. You can't see when I'm using this pen, so let me use my my mouse here. So let's have this first rung corresponding to this input here, input 0. Okay, so this one right here is input 0. Okay, and this is going to be output 0. Okay, so output 0 corresponds to this terminal, which will send voltage to this lamp right here. And then input 0 has this normally open selector switch going to this terminal right here. Okay, so taking a look at this guy, if I scroll out, can we see our notes here? Okay, so taking a look at this one right here, we've got the examine if closed, and that examine if closed looks for the presence of a 1, a true status, 24 volts, or that something is in the on state. Okay, well, let's zoom back in and let's take a look at our wiring here. Get my head out of the way. Okay, so this selector switch right now is open, right? So the status, if we put here on the side here, the status of these bits, right, is that there's no voltage, so there's 0 volts right now going to this input terminal, right? And that means that the status is going to be a 0 in the memory there. Okay, so that means that this instruction right here, this examine if closed, it's looking for a 1 in the memory. So that means that this 0 is going to mean that this is false. So that means that this is false. And if that is false, then there's no way that it's going to be able to send logic over to the output. So the output is also false and the light is off, right? Right now we would have 0 volts being applied to the output, and that would mean that there's a 0 in the memory for that particular bit or output 0. Okay, so hopefully you're seeing that if this particular selector switch is not closed, there's no way for this 24 volts to get to this input terminal. If there's no 24 volts available at that input terminal, there's 0 volts applied, which means the status is a 0 in the memory for this particular input. Okay, that means that this instruction is false. It's looking for a 1 in the memory, but there's a 0 in the memory. So that's false, which means that the output is false, which means that there's no voltage going to the output, and that the bit for that output, output 0 is a 0 there. Okay, if I was to close that contact, sorry, I grabbed it with my mouse, sorry. If I was to close that contact, then everything changes. Okay, give me 2 seconds here just to get rid of everything. Okay, so if that contact then closed, right? So if I had this closed now, then the voltage is now being applied to that input terminal. Okay, and the status of that input terminal would then now have 24 volts applied to the input 0, which means that the bit corresponding to that input terminal right there would go from a 0 to a 1. Okay, this instruction right here is looking for the presence of a 1, so it's now true. If it's true, then the output that's corresponding to it, because there's nothing else in that line, would also be true. So that would mean that now all of a sudden there's 24 volts being applied to the light, and the bit that corresponds to this guy right here would then change from a 0 to a 1 to reflect that. Okay, as soon as I open that contact, so sorry that this takes a little bit of time to dry in. If I was to then open that contact, then we're back to where we were before. Right, that contact is open, which means that there is 0 volts applied to that input terminal. The bit just changed to a 0. This is looking for a 1, so this is false, which means that this is false, which means that this output here is then going to go to 0 volts, and the bit that corresponds to that output 0 changes to a 0 as well. So it's an examine if closed, but think of it when that specific selector switch is actually closed, then the voltage is applied to the terminal, and it's the voltage that's applied to the terminal that determines the status of that particular bit. Okay, hopefully this is helping. Let's take a look at the next guy right here. So let me get rid of the status of that first bit, and we're going to use the next instruction, the XIO below, So we're going to have this guy corresponding to this second rung in our PLC program. And then the output that's going to correspond to that is going to be output 1. Okay, so we'll say that this here is input 1. This is going to be output 1. Okay. And let's walk through the same steps there, guys. Cool. All right, so at the moment, we're looking at this guy right here, right? So that's a normally closed selector switch. And if that's closed, that means that if we don't touch that selector switch, then the voltage that's available here from the 24-volt power supply will be able to go up through that switch and be applied to that input terminal number 1. Okay, so the status of that input terminal would mean that there was 24 volts available on input number 1, and the bit that corresponds to input number 1 would go from a 0 to a 1. Okay, this instruction right here is an XIO. If we take a look at the XIO looks for the presence of a 0 in the PLC memory. Well, right now we don't have that. We have a 1. Right? It also looks for the presence of 0 volts. We don't have that. We have 24 volts. So for those two reasons, then that particular instruction in our PLC program is going to be false. If it's false, there's nothing else in this rung, so the output is false. So that means that this is false and the light is going to be off. Right? So we're going to have 0 volts applied to the light, and the bit that corresponds to output 0.1 is going to be a 0 in the memory. Okay? If we took that contact and we then opened it, okay, that means that on that input, so input number 1, we now have 0 volts, right, because we blocked that current going to input number 1. The status would then change from a 1 back to a 0. And this instruction right here is looking for the presence of a 0. Well, we definitely have the presence of a 0. So that is true. So that's what's a little bit messed up, is that you have instructions that are looking for the lack of a signal. That lack of a signal is being seen here with a 0 in the memory. Okay? This instruction is looking for the presence of a 0. We clearly have a 0 in the memory, so that is true. There's nothing else in line with the output, so the output's also true, which means that this fires on and the light would be on at that point, which means that 24 volts is now applied to from the PLC over to the light, and for this particular output bit, that bit has changed from a 0 to a 1, showing that its status is true, that there's 24 volts applied, and that it's on. Okay, so hopefully you're seeing the different instructions and why you may or may not use each of those instructions in different setups. And you're also seeing that it really doesn't matter the way that the individual input is wired. Like you can have it normally open or you can have it normally closed. You can change the logic of that switch because you're looking at whether the switch has a 1 or a 0 being applied to the memory of the PLC. Okay, so let's bring this guy back to that original status. Okay, so that guy was closed. Okay, so let's take a look at the stop and the start now. So this may bend your mind a little bit, especially if you've been taught the opposite of what I'm going to show you right now. Okay, so this one here, this stop, is going to be wired to input 2. Okay, and the start is going to be wired to input number 3. Okay, the output here, I'm just going to use the next one, output 2. Okay, and what's messed up is I'm going to have this contact right here, not messed up, but it's different. This guy right here for my holding contact, I'm going to have it corresponding to the output. So I don't have anything wired to the PLC to actually see that the output is on. I'm just going to use this instruction right here to look at the status of this particular bit in the output terminals. Okay, so I'm going to correspond this guy to output number 2. Okay, again, it's looking within the PLC. It's not looking externally for a signal. We'll deal with that later on with external signals. Okay, so my stop switch on input number 2. Okay, so this one here is my stop switch. So stop push button. This is my start push button. Okay, and we can see here that on this guy, the stop is closed. Okay, so I've drawn it hopefully so that these guys are making contact. And that means that this 24 volts, as long as I don't touch that push button, this 24 volts is being applied to that input terminal, right? Because this contact is normally closed. So current has the ability to go from the positive of the power supply through the normally closed and into input number 2. Okay, so that means that there's 24 volts applied to input number 2. Okay, I'm going to put 2 here and 3 here. Okay, if there's 24 volts applied to that terminal, then the status is that that bit that corresponds to that input number 2, is now changed from a 0 to a 1. Okay, so it's true. Okay, this instruction right here is looking for the presence of a 1. I clearly have a 1 because I have 24 volts applied to that terminal. So this instruction is true. Okay, let's move on to the start push button. Okay, the start push button, at the moment, if I haven't pressed anything, there is 0 volts applied to input terminal number 3, which means that the status is that there's a 0 in the memory. Okay, I have not pressed this push button, which means that there's no way that this voltage can get to this terminal. So that means I have 0 volts and a 0 in the memory corresponding to that. So even though the stop push button is true, the start push button is false. And so I need to have true status right across. So that means that my output for number 2 is off and the light is going to be off. So that means I have 0 volts at output number 2. So let me put these guys in brackets so you know what I'm talking about. Okay, and that means that the status of that guy is a 0 in the memory. Okay, well maybe I have a way around that start push button with this holding contact, as long as this instruction corresponds to this guy being true, but it's not, because this instruction right here looks for the presence of a 1 in the memory. At the moment, I have a 0 in the memory, so that means that this instruction here is also false, because the output is off. Okay? So at that point, nothing's happening. I have to have the stop push button and the start being true, or I have to have the stop push button and my output 2 holding contact being true in order for the output to actually be true or be on. Okay, so let's push the start push button and change the status of that bit. Okay, so let's get rid of these guys. This, and these are going to change state now. Okay, so our start push button, okay, I'm now going to press that push button, which means that the voltage is going to be applied to input terminal number 3. Okay, so that means that input terminal number 3 is now going to go from 0 volts to 24 volts, and the bit that corresponds to it will now change to a 1. We haven't done anything to the stop push button. The stop push button has not been pressed, so it is still true. There's a 1 in the memory. This one's looking for a 1, and so this is still true. Now that we've pressed the start push button, now we're looking at this instruction right here. It's an XIC. That XIC is looking for the presence of a 1. Well, it now changed to a 1. So this guy is now true. So now both instructions, input number 2 and input number 3, that are both wired differently out in the field, but are using the same type of instruction, are now true. If they are true, then the output 2 is now true. Okay, which means that this guy's on and this guy's on, which means that there's now 24 volts being applied to the light, and the bit that corresponds to output number 2 is now changed to a 1. Okay, if the output bit number 2 has changed to a 1, then this instruction is now true as well. Right? It's seeing that the output 2 is true or on, or that there's 24 volts being applied to that load. We can't look at the load, like we're not physically looking at the load to see a contact closing. We're just looking at this particular bit to see that it's a 1. So again, we're not looking at an external contact that corresponds to output number 2. We don't have any other inputs that correspond to this coil there. So we have no external confirmation that it's on. We're just dealing with the bit that's internal to the PLC that has gone from a 0 to a 1. Okay, so that means that if hopefully you're following this. I mean, it makes sense to me, but hopefully you're following this. As soon as I'm going to open that start push button. Okay, so I'm going to let the spring bring it back up, and that means that there's no longer voltage being applied to input terminal number 3, which means that this is now changed to 0 volts, and the bit that corresponds to it is now a 0. Okay, that means that this particular bit right here is now false. Right? It's looking for the presence of a 1. There's no longer a 1. There's a 0 in the memory, so it goes false. But the output terminal number 2 is still on. Still 24 volts, still a 1 in the memory. Okay? That's because there's a path here through the stop push button, through this holding contact, and then to this coil in order to keep a path of logic continuity. Not a path of current, but a path of logic. This is true, and this is true, so this must be true. Okay, so it's not the path of current, it's the path of logic. Okay, so even though the start push button is no longer being pressed, the stop push button has not been pressed, so it is true. The holding contact is true because there's a 1 in the memory there, so the output terminal number 2 remains on. Okay, everything's cool until I press the stop push button. Okay, so if I press the stop push button, let me just get rid of a couple things here. Okay, once I press the stop push button, then things are going to change. Okay, so I'm going to press that stop push button, which is going to open that contact. And as I have that contact open, there's no longer any voltage applied to input terminal number 2. Okay, that means that 0 volt is applied to input terminal number 2, and it's now gone from a 1 to a 0 in the memory. Okay, that means that this path of logic continuity is gone. So let's get rid of these guys. Okay, we know that the start push button is false because there's 0 in the memory. This is looking for the presence of a 1. There's no longer a presence of 1, so it's false. We press the stop push button. It was true, but it's looking for the presence of a 1. That instruction looks for the presence of a 1. There's no longer a presence of a 1 in the memory, so this instruction right here is false. Okay? Those two are now false, which means that the output turns off. Okay, so that means that this is off and this is off, and if we take a look at the voltage on the output, it's now changed from 24 volts to 0 volts, and the bit that corresponds to output number 2 is now a 0. If the bit that corresponds to output number 2 is a 0, then this guy is also false. So this path of logic that we had from the stop through this holding contact to the output is now eliminated, right? It's gone. Okay, one more step. Now I'm going to let go of the stop push button. Okay, so that means that once I let go of that stop push button, then the voltage is available to go to that input terminal. So I'm bringing everything back to the rest state. Rest state is this guy's closed. Okay, so there's voltage available at input number 2. That means that 24 volts is applied there, and there's a 1 in the memory. That means that this instruction here is true, but the other two instructions for the start push button and for the holding contact are both false. So that means the output 2 remains false as well, which means that this guy's false and this guy's false, and that means that we're remaining with 0 volts applied to the output LED there. So hopefully that walks you through the sequence of events for a standard 3-wire and the difference between an XIC and an XIO instruction. Okay, guys, let's take 5 minutes and let's go back to our Studio 5000, because at the moment it's angry at us. So we've got to put in our individual bits that correspond to those inputs, right? We'll do the same as we have on our diagram here. So the first one will be input 0 and input 1. And then for my start holding contact, I'm going to have input 2 and input 3. But let's go back to our Studio 5000. Let's quickly put in our inputs here. So I'll show you how to do that. We'll download it to the PLC, and then we'll walk through the same sequence of events, and we'll see whether there's voltage or no voltage at the outputs there. Okay, so this one's turning out to be a little bit of a longer video. Sorry about that. So let's go through and put in our instructions here, because it's angry at us clearly because it's all red right across, right? So what we're going to do is we're going to click on here, and then we're going to click. So what I did that a little bit too fast. I'm double clicking on the empty operand here. Okay, so that for me that was a double left, could be a double right on yours, you'll see. And then I'm scrolling down until I find local 1:I. That's my inputs there. Okay, we talked about that before. And we have false data and we have readback. So we're looking for the data here. So I'm clicking on this guy. And then hopefully you can see that there's this little arrow that's there. So we're going to click on that bad boy. And then it's going to give us 0 through 16, right? So we have our word of data there. I always like to say word. And we're looking at the individual bits. So for this first input, we had input 0. So we're going to grab this bit right here. Okay, and it's still angry with us. Let's click somewhere else on the screen and see if it works. Beautiful. Okay, and then I can go down here, and then what do we have here? We have edit properties. We're looking for something where we can put in a description. Edit main operand description. So let's click that. Okay, and then we're going to type in that one on our diagram. Let's go back to our diagram here. That one was a normally open selector switch, right? Okay, I lost that here. So main operand. So normally open selector switch. Beautiful. Okay, so now it's good. It's not angry with us with this one, but we need to put in our output here. So again, I'm going to double click on the empty operand. Okay, then I'm going to click on this arrow. Then I'm going to look for my outputs. So I have local 1:O for my outputs. I'm going to click on this arrow beside. Okay, that brings up the data for the outputs. I'm going to click on this guy. Then there's a little drop-down menu that appears. So we're going to click on that guy. And that one is going to be output 0. So I'm going to use this bit right here for output 0. Okay, nice. So now the whole rung seems to be happy with us. We don't have a name for this guy, but I'm just going to click on this guy, do edit main operand description. And we're just going to put output 0, if I can spell. Beautiful. Okay, we're going to do the next empty operand here for this instruction. If we go back to our diagram, that one was a normally closed selector switch. So we're going to click here. We're going to our inputs. Okay, we're going to data, clicking on data, bringing us down. Now I could type all this in, but I'm just lazy. I like to go to the individual bits. That one is going to go to input number 1. Okay, why is it going to input number 1? Oh, you can see that that one went true right away. Why is it going to input number 1? Because we wired it on our diagram to input number 1. Okay, so that's good. Let's give it a name. So that guy was a normally closed selector switch. Okay, yes, or was it, let me see, can't remember. Yeah, we had normally open, then we had a normally closed here. Okay, looks good. Okay, this one here, we're going to use our output. So we're doing local 1.O, clicking on this arrow, come on. Then choosing our next output, so output number 1. And we're going to click on this, edit our main operand description, and we're going to just type in output 0. Output 1, sorry. Okay, so this is our first output, our second output, but remember everything starts at 0, so this is output 0. Output 1, following along, this would be output number 2, so let's finish that guy off. So number 2, it looks like it's showing that 2 are used, right? This is not in use yet. Okay, and we're going to change the description there. So that's going to be output number 2. Looks good. Okay, and then where did we wire our stop and our start switches? Looks like our stop went to input number 2. Okay, so we're going to click on here, looking for the inputs. Okay, looking for the data. Okay, so input number 2 looks good. We're going to edit the main operand description. Okay, and that's going to be our normally closed stop push button. So normally closed meaning that it's physically a normally closed push button, right? Okay, then for this guy, for our start push button, we're looking for our inputs, data, and that one is going to input, excuse me, input number 3. Whew. Okay, let's just make sure that's cool. Yeah, start was going to input number 3. Looks good. Change that guy. Hello. So that was a normally open start push button. Okay, normally open again, meaning that it's physically a normally open, not the instruction, right? These are both XICs. And then here, I'm going to correspond this one to my output number 2, right? So we're going to our outputs, right, on this word and this data, and we're looking for bit number 2. Okay, and then hopefully when we click somewhere else, it should give us the same description there for output number 2. Beautiful, looks good. Okay, so let's download this to our PLC. Okay, it looks good. So now I'm talking to my PLC through the Ethernet connection. So I'm going to download this new program. Excellent. Now we're going to bring it back to the remote run. So we'll hit yes. Nice. So now you can see that all of the bits are coming in here. We can see the status of our 2 rungs here, and we can see the status of this input, and these guys here as well as the output terminal here for output number 1 there. Okay, so give me 2 seconds. Let me set this up so that I can move this program over and then show the PLC as well. Give me 2 seconds here. Okay, so let's set up all of our inputs the same as we have on this diagram here. So input 0 is going to be a normally open selector switch. So I've got a number of different selector switches here that correspond to those inputs. So I'm going to leave the input 0 in the open position. Okay, input 1 is going to be a selector switch in the closed position. So I'm going to move it over to the left-hand side. Again, with these selector switches, I have the ability to do like a momentary contact here and a maintain contact to the opposite direction. Okay, so input 1 is now closed, and now the stop push button, which was input number 2, it's going to be closed, so I'm going to leave that in the closed state. Okay, and then the start push button I'm going to leave in the open state there. I'm also going to show you how I can use jumpers to go from my positive power supply into each of those individual inputs. But let's start off here. And right at the moment, I've got the meter hooked up to output 0. So that's going into the, you can just see here, that's going into the common and the voltage input on my meter. And I've got my meter set to DC volts. A little bit of a glare on the meter. Hopefully you can see that properly there. Okay, so right now we've got no voltage, and you can see that the LED that corresponds to that output on output 0 is not illuminated yet. So let's go to our program here. Okay, so we have a normally open selector switch, but this instruction right here is looking for the presence of a 1. If I hover over this guy, let's see if we can hover over it. So you can see here, so hard to see, it disappears right away. But the value, if you look on that, it says tag element, then element data type, which is Boolean. Then it says tag data type, then tag scope, controller. And then finally it says, like third from the bottom there, it says value of 0. So in the memory, it's providing you with the value. It's a 0 in the memory, and that instruction is looking for the presence of a 1, so it's not true. You can't see the output. Hang on, let me make this a little bit smaller. Okay, cool. So at the moment, we can see that output 0 is off, right? Because this is looking for the presence of a 1. There's a 0 because the contact is open. So what I'll do is I'll change the state of that input, right? So I will change that to a closed status. And now we can see that the output is on. So the LED corresponding to output 0 is on. We can see that this guy right here is on. The green denotes that it's true or on. And if we hover over that guy, come on, we should be able to see the status. And you can see the third value from the bottom there. It says that the value is a 1 there. Okay, so it is a normally open selector switch. I've now closed it. There's 24 volts at the input 0. This is looking for the presence of voltage or that it's true. So that's true. It turns on our output, and you can see here that there's 24 volts now available at the output. If I change that status back to a 0 or 0 volts, let me get this out of the way, then you can see that the output has turned off. And if we hover over it, then the status of the value, so again, third one from the bottom there, you can see that the value is 0, and you can see that the voltage has now gone to 0 as well. Okay, let's take a look at the second rung here. So we're taking a look at this guy right here. Let's change our meter over to output number 1 now. Okay, so right now we can see that the output is off. If we hover over this guy, then we can see that the status, come on, the value is 0, so it's off, and we can clearly see that there's no voltage at the output, and the LED that corresponds to it is off as well. So that's because this instruction right here is looking for the presence of a 0 in the memory. And if we hover over it right now, the value, so I wish I could like show you with another mouse, but the value, so taking a look at the box that's just below there, the value says 1. Right, so there's clearly voltage being applied to input number 1. You might just be able to see that this LED here for number 1 is on with that voltage. And if I change the state of that, then it's now a 0. So you can, I don't know if you can just make out this LED, this tiny LED right there, right? So there's voltage applied to the terminal. There's no voltage applied to the terminal. So this instruction right here is looking for the presence of a 0. I have now pressed that selector switch, right, or changed the state of that selector switch. So now the value is a 0. So this is true. So now the output is on, and we can see that there's 24 volts available, and we can see the LED is illuminated there for output number 1 as well. Okay, so hopefully that clears up the 2 instructions. Now let's take a look at the 3-wire now. Okay, so now let's take a look at this final one here. So that's my normally closed stop push button. Okay, so I'm on this rung right here. I have that input here for my stop push button. I have it closed, so it's like nobody's pressed that push button. Okay, and you can see that its input is coming in right there for input number 2. Okay, so it's looking for the presence of a 1. If we hover over it, we can see that the value there is a 1, so it's true. So now we can see that the output number 2, let's move this guy over to output number 2 now. Okay, we can see that clearly there's no voltage available there, and there's no LED on there. So we're waiting on someone to press that start push button. So let's do that. That's input number 3, right? Let me get my fingers out of the way. So input number 3, I'm going to move to the side here, right? So that is like me pressing the start push button, okay? And once I do so, then we can see that this instruction and this instruction are true, right? If I hover over this guy, Come on. No, it's not giving me the status. There we go. That's a value of 1. And the output is clearly turned on. There's a value of 1 there. And we can see that there's 24 volts available. And we can see that the LED is showing us that output is on. And we can also see that the output number 2 on this LED is clearly showing that it's on as well. Okay, you can see that I've now let go of that push button, right? So that start push button was pressed. I let go, but the output is still on, right? The value for this guy is still a 1. There's still 24 volts being outputted to the to whatever device that we have connected to output number 2. Okay, so the path of logic is here. This is true because it's looking for the presence of a 1. There is a 1 there. This is looking for the output being on or true or having a 1 in the memory. And we can see there the third one from the bottom there, the value for output number 2 is a 1. So this is true, which means that the output is on. The only way to change the status now of output number 2 would be to open up our normally closed stop push button. So let's do that here, right? So we will change the status of that input, right? So now the normally closed stop push button is no longer true, which means that the path of logic has been blocked and our output turns off, LED is off, and now there's 0 volts at that output, okay? That stop push button would have a spring, so the stop push button would go back to its closed state. There's 24 volts applied there. Its status is a 1 in the memory, so that instruction is true, and it's again waiting for us to bring a momentary pulse to the start push button to turn on the output. So momentary pulse on the start push button, turns on the output, let go of the start push button, the output remains on until we hit the stop push button. Okay, so hopefully that clears up the difference between an XIC and an XIO and different ways that you would use both an XIC and an XIO in your program. One looking for the presence of a 1, the other looking for the presence of a 0, and why on certain switches like a stop and a start, the stop being a physical normally closed and the start being a physical normally open, that we would make use of the exact same type of instruction there within our PLC program in order to get the logic that we're looking for in order to turn on our output there. So hopefully everything makes sense. If it didn't, you're definitely going to leave comments in the comment section below. I've tried my best to describe why I've used an XIC there. You will see other people that use an XIO. That's just because they have made use of a different type of physical contact right there. Instead of using a normally closed, they would have made use of a physical normally open stop push button, which you don't really see, or would maybe on an emergency stop or something like that. But I'm going to leave it there because I'm going to get you even more confused. So hopefully everything has made sense, guys. I will see you on the next video, and we'll continue on with a little bit more PLC programming. Thanks very much. Thanks for sticking with me with such a long video. We'll see you on the next one, guys.